Welcome to the last session of this meeting, and this session is dedicated to method developments, and our first speaker is Professor Zhou from UCLA, and he will tell us about structure of viral genomes.
Thank you so much. Well, thank Steve and Moses for the kind invitation for me to come here. Really enjoy very much so far. So you heard a lot so far about this very high resolution structure of proteins, some nucleic acids, about the RNA. But a bit from Arena's talk about the attempt about to resolve the genome of viral genome. So I thought as a presenter in this particular session that focus on sort of methods, I thought I'm going to give you a couple of examples to illustrate really that the new technology of the direct electron detection can new opportunities offer really by this new technology in terms of resolving genome structures. So I will start from here. Of course, everybody know about this picture. Of course. This is the Watson Crick. Look at the structure, the model of the first genome structure, which was published about 65 years ago, a long time ago, based on other data. Rosalind Franklin, of course, you all know that. It turned out, if you read into the literature, history about this very important work, you'll know that Franklin actually started about the same time with Casper. We all know, for the first of all, we have a season enough in EM. You know this Casper, Don Casper, who with Rosalind Franklin tried to resolve genome structures of viruses. Shown here is the model of the RNA virus, the TMV, showing the model of showing a little Casper model of a little bit of RNA genome of the TMV. You haven't seen much since then. Okay. I looked very hard. I could not find much in the literature about genome structures. The reason behind that is because those are hard to do. For obvious reason, because the genome structure is pretty flexible. If you want to grow crystal, you just don't grow crystal. If you take images, they're very hard to see them. We actually tried very hard in the lab, tried to resolve the genome structure in the old days, by EM. And then we have difficulties, mainly because the contrast of the image is so low. So we won't be able to learn much with by EM methods. A few years ago, you all know that you have seen so much in this meeting that the great thing about the direct electron counting technology in EM is that it really, to my physics mind, is that it often offers this what I call quantum efficiency, because once you can count electrons, that's the best you can do from my physics point of view, because you count it. That means you don't have noise. Everything you see, you count it, is the signal. So that's probably the best you can do. Indeed, if you look at this is an image of a virus. You'll see that these are the features of the genome in the virus is so prominent, it almost jump at you. So, so that was so amazing. Then we thought maybe we should revisit the same topic about trying to resolve the genome structure. So that's how this gets started. So as you have all seen, viruses actually provide a very good opportunity in old days, even before the direct electron detection technology came about, for us to push the technology of cryo-EM to near atomic resolution. Shown here is one of the early structures we did on this double-stranded RNA virus called real virus. You can see these are multiple shells of protein, and then we show that you can resolve amino acids, and also in this particular case, we can resolve what we call lipid moiety, which called fusion finger of the virus. So one of the things you have seen many times in this meeting is that cryo-EM is great because you can actually work on native things. That means things that have this strange attachment modification, and things you don't want to work with in the old days by crystallography, but now this actually is an advantage. You can actually look at them and being able to model them. So, so what I want to focus today is instead of going outside, but focusing looking inward in the virus to see whether we can resolve the genome inside the virus. I would argue that, again, similar to the argument I made about the protein, so viruses offer a great opportunity for doing that because you maintain the native structures inside. That, to me, probably offers the best opportunity to resolve the genome structures. So you don't interact with the structure inside. So, and then perhaps you can resolve the native structure. More importantly, perhaps you can also do some experiments with the intact virus structures, which I will show you in the second example, how actually we take advantage of this and try to trigger the virus to replicate transcribed RNA and try to resolve this. So start with a simple example. So this is a single-stranded RNA virus called bacteriophage called MS2. We chose this for two reasons. First, it was the first organism being sequenced many years ago. And second, it has a very, very small genome. It has a genome of only about 3,600 bases. Now, it's a single molecule inside. And then it has a crystal structure of the coat protein shown here, done in 1990. And in this crystal structure, it shows an icosahedral protein shell, as shown here. But it's missing a very important protein in addition to the RNA genome, which is this was called a maturation protein. And that is a very important protein because, as the name implies, it's important for the virus to package the genome and also to mature the virus, and also for the virus to deliver the genome into the host. So it's a very important protein. It was not visualized before, and then so we thought maybe this offers a good opportunity not only to resolve the genome structure, but also to understand how the genome is organized and deliver into the host. So just a little bit background information. So this is the virus. This is a phage. So in fact, the bacteria E. coli is shown here. So you hijack the F pillars, which is those are pillars. You can see these are also called sex pillars because this is how the E. coli exchange genetic material. But anyhow, the virus hijacked the process by way of attaching to these sex pillars of the cell, bacterial cell, and then these things then pull the pillars, and then the virus genome magically got delivered into it. And the process is not understood. The structure base is not understood. So hopefully by doing the structure together of the genome and the maturation protein, we hope to understand how this works. So, so this is a structure of the virus. It's from about 50,000 virus particles. So, the structure is determined about 3 angstrom resolution. As you can see, that the typical structures, you can see the side chains of protein, and there's one copy of the maturation protein, which is shown in purple here. More importantly, if you cut open this structure, you can see that inside the virus, you can see these very characteristic, the groups, RNA groups. These are stand loops structure of the RNA. So you can, in addition to protein, side chains is shown here, and here is the genome structure. You can see that some of the bases can be evenly resolved, and other regions of the genome, then they are, although they're visible, but they're not as well resolved as regions like these. Just to show you the original data, so you can see that this is the original map. Looks symmetrical, but if you look carefully, there's one copy of the protein which is right here. It's sticking out, but this is that maturation protein, which is different from the other co-protein. And this is filtered to about 6 angstroms, so you can see better about the features. And if you cut open, then you can see the genome structure inside. You can see the, these are the major amino groups, but you can see all those branches of the folded RNA genome, and those are regions of the interactions of the RNA. And it's very important to keep this in mind because that's actually related to how we model the genome afterwards. So obviously, the structure is not sufficient for us to build atomic model for the entire genome. But we take advantage of those things that's visible, high resolution stand loops, and then together by sequence-based structure prediction. So those turn out the secondary structure prediction of genome RNA is very reliable nowadays, about 90% accuracy. So you can take advantage of this prediction tools as shown here, and then you can figure out all the stand loops, okay, and then and try to map these stand loops, and then take advantage of the visible those high resolution stand loops as shown here, and then we are able to model about 80% of the genome sequence. So we for regions that is lower resolution, we can only trace the backbone. And for regions of the interacting with the protein, we can model atomic details as shown here. So this is the model of the genome. So this is one copy of the maturation protein MP is shown here just for reference. And those regions are the high resolution stand loops, which we model at atomic detail. As you can see that the distribution of the stand loops are asymmetric. They are more towards the MP protein, less on the opposite side. And so there are lots of interactions between maturation protein as shown here. And these stand loops are all interaction with the other co-proteins. So if you look at those high resolution stand loops, then you can identify some patterns of these interaction features. So it's shown here. This is a stand loop region interacting with the co-protein. So you can see that they form these very characteristic interactions. Turn out the patterns seem to have always AU and A with a spacer about 3 to 4 bases in between. Shown here. So this shown here is this is one example. You can see that this interaction. And then one observation that we made is that the interaction between the co-protein shown here and the maturation protein, between maturation protein and the genome is much more substantial than the interactions between the genome and the co-protein, so which are shown here. So more than 20 interactions between the maturation protein and the 3' end of the RNA stand loops. As I said, these are the pattern of the interaction. So we identify where this is, and there is because the virus, the phage has been studied substantially, and then there's also a tomography structure done by Dent et al., published in 2013, where it shows how the virus attached to the sex pairs, as shown here. And so we can place our atomic model of the virus together into the tomograph. So you can show that this is looking from the pillars rotated 90 degrees. You can see how this is attached. One thing you can see that it's roughly tilted, which is corresponding to the maturation protein right here. And then there are 4 pieces of evidence in the literature that can be integrated together to interpret what we observe. So first is that binding to the detached pillars itself does not trigger genome release of the MS2. So the binding itself does not release the genome. Secondly, if you have MS2 as a virus binds to the pillars, and then you can always cause infection. The genome can always enter the bacterial cell. Thirdly, if you simply mix MP with the genome, okay, you can also trigger the genome delivery. And it means that the co-protein is not required. Okay? So if you put all this information together in our model here, then one thing you can come forward is the genome seems to be delivered the following way. So somehow once the virus is attached to the pillars, as shown here, and then trigger the pulling of the pillars by the host cell, which is a response of the pillars, and then because this is very high interaction between the maturation protein and the genome, and then and very little interaction between the co-protein and genome. So this will somehow peel off the co-protein due to the size, the diameter, limited diameter of the structure of the here, the basal body here. Then the genome will be somehow hijacked and delivered into the host cell. So this is how we can come up with a model about based on the observation of the EM structures. So this is so we demonstrate you can actually model the genome. So the second thing, second example I want to show you is that how we can even go further. So the example I want to show you today is a double-stranded RNA virus called CSP-B, and this is a virus in the family of the Viraridae. It's double-stranded, and it's only a single shell virus. Again, this is the simplest member of the virus family. And another prominent member of the virus family is rotavirus. Many of you have heard about it. So all these viruses in this family share this characteristic mechanism of what's called endogenous RNA transcription. Basically, the virus, you can actually trigger the virus to replicate and also transcribe the genome in the absence of a cell. So you can do the experiment on the EM grid. So we thought this is a great tool. So you can actually visualize not only the genome but also the genome in action. So I'm going to show you 2 structures today, given the limited time. So first one, just want to show that you can tell you that you can actually do this thing on the EM grid. So what I show you here is a CSP-B is undergoing transcription. So if you put the virus in a solution, you can provide all the NTPs and the enzymes, and then the virus can start transcription. So it turned out CSP-B, this very great property of CSP-B has actually contributed to some fundamental discoveries in biochemistry. Shown here, this is Frocho et al. 1974, and again 75 together with Shakin, and they published some of the first observations about how the RNA capping occurs, and this is based observation on CSP-B. So at that time, of course, they didn't have the EM. They have to make that observation based on radio activity, things like that. But the bottom line is that we can do the same thing today. We can operate that kind of experiment on the EM grid. So this is the structure that we published years ago, and this is a structure, a 2.9 angstrom of what we call quiescent, which means that you do structure without adding the enzymes and the NTPs. So the virus is not doing anything yet. So if you release, don't impose a symmetry and do an asymmetric reconstruction, and then you get the, before I get to that, so I just want to show you some details about the structure. So this is a single shell protein, so it has a single shell virus, 3 different kind of protein, and they 5 unique conformers. So these are the 5 unique conformers in a asymmetric unit. So this capsule shell protein and terra protein right here is 1 copy called TP, and this is the multi-enzyme capping enzyme. One of the things before I get in detail is that this virus achieved that stability with a single shell through this unusual, very unusual structures. This is what we call N-terminal anchor. So you can see that it has a very extended N-terminal sequence segment. If you put this together in the context of the virus, you'll see that this N anchor goes along across multiple copies of proteins. Different color here represent different subunits of the CSP. You can see that go through 5 different proteins and form what I call this augmented beta sheets. The same mechanism across different proteins. This is one of the things you have seen so many times already in this meeting, that looking at the structures together in a native form provide this great opportunity to see these extensions, which may not be able to be visible if you actually do a crystallography of the single protein. And these are the things normally you just truncate, and these are probably the most important areas of the protein. So this is this is another example in the CSP-B. So, and of course, I mentioned this other protein of TP, which is the multi-enzyme complex, or the capping enzyme complex. So those structures all resolve atomic detail. And then very important to understand what I'm going to tell you in a moment. So keep in mind, this is a multi-enzyme complex. And early on, based on aqueous visual reconstructions, we know that this is how things work, because this is where the genome releases, and then on the way out, the genome will be capped. So if you take this same virus, now of course it's much better contrast with the direct H1 detection. Then you can do an asymmetric reconstruction. So you can determine the orientation based on the internal structures, not the external external co-proteins. This is one. So this is how we did it. So basically, we do a aqueous visual reconstruction first, and then do something similar to what you already heard from Shores and others, similar to the focus refinement. So you subtract the outside contribution in proper way, so that there's no ghost shadow in the subtracted image, and then use the internal structures information only to obtain a structure of the whole thing using the whole data, unstructured data. So you'll see both the inside and also the external structures. So once you did that, you can see that this RNA genome will be visualized. In addition, one thing I want to point out to you is that you can see these other non-RNA structures. These are protein. Turn out this is a transcriptional enzyme complex, TEC. So this is the viral polymerase. You already heard from Chris this morning. And so this is much simpler situation. It turns out, if you look at this carefully, there are only 10 copies of those. So although there are 12 locations in the virus, there are only 10 copies. So which I show you here. They're in the equivalent location like here. This is the equivalent location. There's no polymerase. This makes sense. This virus contains only 10 segments. It's a segmented RNA. There's only 10. So each segment has 1 copy of the enzyme attached to it. So again, if you zoom into that region And then we can resolve that structure in a much better resolution. You can see that this is the capsule shell. You can see this polymerase complex TEC attached to the shell. And you can, of course, see the side chains of the protein. You can see also interactions between the shell of the CSP and the protein. There's a little bit of density of the RNA in high resolution. They're not very well resolved, but if you filter this structure to low resolution, you can see the interactions. So this is, again, this is the RNA. This one is one double-stranded RNA is making contact with the RNA-dependent RNA polymerase right here. And then one thing we observe is this additional protein called VP4, which is totally unexpected. Okay, but what is found complex with it in the TEC, and we recognize it being a VP4 based on the sequence because the side chains are good enough. So we actually identify this protein based on the side chains, and this protein, if you look carefully, which is shown here. So you can build a atomic model, and then one thing I'm pointing to you that there's one region here that right here, extra density. That we cannot account for, and then we eventually recommend you sort of guess maybe either ATP or GTP, which I can't tell, and then so we suggest that it's an NTPase. Okay. We don't know the function. It's making a contact with the polymerase. So that's the curiosity structures. So now we're going to do the same structure now doing the experiment on the grid. So we're going to see the same thing with all the NTPs added. You call this TCP-B, transcribing CPV particles. So you can see the same density here. And then the structure is a little bit lower resolution, about 4.2 angstrom resolution, but you can see the structure is sufficient to build atomic models. So this is that, again, the comparison of the TCP-V and the QCP-V in the polymerase structures. You can see that if you focus on the polymerase only, then you'll see that the polymerase structure, the viral polymerase, has the canonical polymerase structure that we have already heard this morning from Chris, but it has this additional purple ring, which you call a bracelet, covering the entrance, the binding side of the RNA. And if you put this together, and then there's some major conformational change between the two. The first is that the bracelet domain, which is here, comparing the two different conformation, one is in purple, the other one is in gray. You can see that there's a major conformational change in the QCP-B. The entrance right here to the channel is blocked, okay, by this. In the transcribing, this is open. So in addition to that, if you look at the other domains of the polymerase, you'll see there's conformational change, mainly that the fork is open up, as shown here, right here, and then of course there's also additional other conformational change during the active site. So we have done 4 other structures basically by looking at the structures at different states. For example, you can add only 1 NTPs or 3, and then you can actually have the reaction stop at a certain stage and make observation of structures. But I don't have time to tell you about this, but I want to just simply conclude by saying that so with this great contrast offered by derivation counting, really cryo-EM offers a new tool for looking at the genome structures. I'll show you by way of the RNA genome in viruses. I'll first show you in the bacteriophage MS2, we are able to model about 80% of the genome, single-stranded genome. And in the case of of the double-stranded RNA virus, we're able to look at different transcriptional states of the viral genome transcription and suggest mechanism of action. So with that, I would like to acknowledge people who contributed to the work. Xin Zhang, who did the Xin Zhang, Xue Keyu, and Ke Din did the most of the work of the CSP-B work. And both of these two guys are unfortunately leaving. This is already gone, and this is leaving the lab. Actually, also gone last week. And so, and the MS2 work is done by in collaboration with Ranson's group at UCLA. And with that, I'm going to just stop right here. Thank you so much for your attention.
Okay, thanks very much for a great talk. We have time for a few quick questions.
Right here, Eva.
Hong is so spectacular. So for this transcriptional machinery, you have 10, because you have 10 genomes, and they are in a fixed position with respect to one another, and they were, you show this nice thing with the tropics of Cancer and Capricorn. So what is determining their arrangement? Is this just a steric thing where there's only one way in which you can arrange them, because they're not following the symmetry of the capsid, but they are in exactly the same position one with respect to the other?
Yeah. So I had an assumption before even I did the work, which is I was trained as a physicist. So anything that you observe, they should be the minimum state, energy state. So there's no exception for genome. There should be some stable structure for it. And in the favorable situation, you should have a unique one. So in this case, I think the genome is in such a way that it has a unique lowest minimum energy state, and we're able to resolve this. This happened to coincide with the capsids, because that's where things need to get out. I guess natural selection select that, otherwise it will not work.
In the MS2 work, I mean, the fact that you can get a structure of the RNA shows that it's essentially in a unique conformation. Is that true or not? I mean, can you get classes that have a different genome organization?
Yeah, Steve raised a very important question. So what I skip very important observation, which is that if you read our paper, which is just published, we actually have 6 different structures. Okay. We try to we just asked for 14 classes in terms of 3D classification in Vilaon. We did the Vilaon. We got 6 of them. The other ones, they're just garbage.
Okay. Yeah. Well, I actually have another question, which is that genome is very well structured in terms of secondary structure. Do you think this is specific for this virus, or is it going to be found in RNA plant viruses and other viruses? I mean, is there a reason why it should be so structured? Because I can imagine later on when you want to replicate it, that's a problem. You have to unwind it.
Yeah, very good question. Yeah, so the fact actually the multiple kind of structure exists, and we saw these 6 of them, that means they're probably not that stable. The multiple, they're flexible. The 6 structure, they share a lot of similarities. There may be 1, 2 regions, they change a lot, and other regions are the same. So whether this is true for other RNA viruses, probably the answer is probably not true for all of the viruses, because actually we did try to look at other viruses. We have mixed results. You know, some other viruses we have make similar observation. Others we have difficulty establishing a well-defined structures inside.
Okay, last question over there.
Yeah, it's amazing work on the genome. So I'm actually wondering, when I see the structures, there are some loops that seem to contact open regions, single-stranded parts, I guess, in between 2 helical segments, right? So that means that the structure, I mean, the intrinsic sequence already tells about how it has to fold.
Yep.
And Now, my question is whether there's any coevolution between the sequence and the capsid evolution, because those two have to fit together, right?
Yeah. So I think there are two parts of the question. One is that the interaction of the RNA-RNA interaction, those probably are specific. Okay, so we did observe. Actually, we rely on those to build a model because we try to identify which strand loops interact with other strand loops. Now, the interaction between the RNA and the protein, so they resolve with the atomic detail. You can see the basis. That must mean that they're very specific interactions. So I guess those are.
And at the same time, they're coding also, so they have a double function, right?
Yeah, I guess that seemed to fit the property of the protein surface.
Which means there could be a coevolution effect somewhere in between those two.
Yeah, selected that way.
Okay, let's thank Hong again.